Okay, now that we have an arsenal of information and we're deadly, we're going to add another concept into the mix. And that is the fact that related rates assumes there are small changes occurring every variable listed in the function. So we're going to have an inclusion of small changes, and reading is going to be very, very important, which is why I had this one printed out. So we're going to let T denote time. Bam, there it is. Everything that we're going to be doing is changing. Everything. The volume, the radius, the height, the base, everything is changing. So we're going to have to take the derivative of what's time. Time does not appear in the function. Time does not appear in the function. So everything is going to be something over dt. Is everybody clear on that? That's number one. And of course, you have it there to look at it. Then it says once you get it to the derivative form, then you substitute everything that was given in the context of the problem. Is everybody comfortable with that? Pretty breezy. So this the first page was strictly for your reading. I'm going to do some problems. Again, the way my function is something directed to something later on constructed. This is directed or guided. And the language of mathematics is not a drudgery, but a necessity. We x equals x of t, introducing that everything is moving or changing. And we have that t as an unlisted inclusion. And y equals of t. So we have a function x squared plus 4. And dx dt equals 3 when x equals 1. And we want to find dy dt. All right, when x is 1. The importance here is timing at that time. Does everybody understand? At that time when x is 1. So we're going to write our function. And we're going to take the derivative. And now we're going to substitute. That's going to give us the dy. We want dy dt. And this is 2 times the 1 for x times the change in x, which is 3. I listed knowns. It was the equation, which was what they were talking about. And all we're going to be doing is derivatives. Then I substituted what was known. How are we doing? All right. Okay. Now remember what I said. I said in related, everything is related to time. Time. So any time we take a derivative of a related rate, we're taking it on the variable in terms of time, the dt. So what I did was, this is automatic. My variable is x, so that would give me x in of time. You're always given, and that's a good point. Let's talk about that. You're always given one of the d variable over dt. You're given at least one of those values because in what we do here, we're going to have two variables, either the outcome as a variable or and the input as a variable. So you're given one and finding the other change. Am I clear? Muddy clear? Okay. All right. We're going to see. And now you all keep asking me questions. You just keep on talking because I don't have my other guy here. Okay. The original 24 meters of a cube decreases. So is that positive or negative? Negative. Decreases. And this is a what? Rate of change. So there's over a dt. Okay, it's over dt. Decreases at a rate of 5 meters per minute. So this decrease is on, let's see, the length. And a cube means all sides are. In geometry, we use the word congruent. If you write on your notes equal, that is okay with me. Okay, so now, when and x equals 3, at what rate does the cube's surface area change? So now what we need is formula for surface area. All right. So in a cube, how many sides do we have? 6. Right? 6. Thank you. And we know that all sides are the same. I'm going to let x equal a side. Is that okay with everyone? All right. So I'm going to write my formula for surface area, which is the sum of every face on the cube, which is 6. Everybody okay with that? I'm going to take the derivative. All right. We want this guy here, that guy there. Substitute. 12 times the 3 times the negative 5. Is everybody comfortable with that? It's not coming up for me. Okay. Oh, there it goes. So the d SA over dt is going to be a negative. What is that? What is it? 180? Thank you. And this is in meters per minute. And oh shoot, yeah, it's area. Meter squared. Thank you. There you go. I got it. Okay. Everybody comfortable with that? When x is 3, at what rate does the cube's volume change? So we want the dv dt. Volume for a cube is length, width, and height, and it's all the same. So we're going to let, again, x equal a side. Everybody okay? Now we're going to put in what we know. X is 3. And the rate of change of x is a negative 5. It's in cubes, so I'm saying it out loud so I won't forget. And I'll get my calculator. It's negative, isn't it? How are we doing? Nothing hard. You only have 9 problems, and several of them are on a sphere, and a couple are in trig. And again, nothing difficult. No questions on this? All right. I'm sorry. And this problem 24? Oh, it's it just tells you the maximum that it was. Fathom why we would have it. That's a huge, huge device. Something that is specific. And there's a that not address that, did I? All right. All calculus problems, you always have a ladder that's slipping. And I hope no one ever walks on it. and, now, in the real world, it has to do with other capabilities, but this is the one that depicts what is happening here. And also, too, the rate of this change that's happening is almost, should be instantaneous, doesn't it? Should be, kind of, sort of. Well, anyway, let's work on this one. Knowing that this is ridiculous, okay, knowing it's ridiculous. All right. But as you see on TikTok, everything is ridiculous. They'll do anything. It's crazy. All right. We have a 10-foot ladder and it's leaning against a house when its base starts to slide away. So they've got an arrow right there. It's moving this direction. So is it negative or positive? Positive. The change is positive. And we have to identify what is happening for application. By the time the base is 6, from the house, the base is moving away at a rate of x dt. Sorry about that. It's on the base. And it's positive at a rate of 8 feet per second. Okay, think about that. 8 feet in a second. I can't even say, well, okay, 8. And it's, right, second. And crazy. That's what I'm saying. Kind of preposterous in a sense. All right. So we're doing, and that's all we know. We know the base, and we're going to let that equal x. At x is 6, we know it is spreading itself, sliding at 8 feet per second. Is everybody good? Okay. What is the rate of change of the height? Okay, so this is this guy. So we want dy dt at the top of the top of the ladder. All right. So what am I going to do? Well, I'm going to have to find the value of y when x is 6. Okay. So what formula do I use? Absolutely. So let's do that first. Is that okay? I mean, we can do it at the end. But let me do it now. So I'm going to have x squared plus y squared equals c squared, Pythagorean theorem. So that's going to give me my 6 squared plus y squared has to equal 10 squared because we know the ladder cannot change. That is our consistent length. What is that going to be? 64? All right. So we have now that if x is 6, then 8 is y. So we have the two outside values, and we want to find dy dt. So how do I state this now? Well, I can state the equation with what I know. How would I do this? Area? Because it said, oh, that's b is area. No, oh, just Pythagorean. Let's look at that. So we're going to have x squared plus y squared equals some value c squared here. And in this case, we have 100. Here we go. 2x dx dt plus 2y dy dt equals 0. Okay? All right. So I'm going to have 2 times my x was 6. My dt was 8. My y is 8, and I don't know my dt. All right, so I got this number right here. What is that, 96? Yep. Just making sure I don't make a mistake. And this guy right here is 32. I'm going to move over the 96. Oh, it's 16, sorry. I saw a 4 right there. I don't know. Some days. Sorry about that. So I'm going to have 16 dy dt equal negative 96. I'm going to divide by that guy. And I should get a concrete value if I did the problem right. And this is in feet per second. So when x is at 6, then the height is reducing by 6 feet per second. Everybody comfortable with that? Yes? All right. Going to do, at what rate is the area of the triangle formed by the ladder wall and the ground changing then? So now we want what? Area. What is the rate of change of area? Here we go. So we know area is 1/2 x times y. Everybody comfortable with that? So I want dA dt equal to, I'm going to take x first, 1/2 y dx dt. Then I'm going to do my y, 1/2 x dy dt. And we're doing it all at the times that we know. All right. dA equals 1/2, and we said y was 8, and 6 was the change of y, the rate of change of y in feet per second, plus the x was 6, and the change was 8, wasn't it? -6 was what I got down here. Yes. All right, here we go. That's a, oh, I got them in reverse. I did it. Oh, thank you. But that makes a huge difference. I did the y and I immediately did the dy. No brains. Thank you. So this is 64, so that makes it 32. And this is a minus 36 divided by 2 is what, 18? Yes? What do I have here, folks? 18. And this is area. So it is feet squared per second. Okay. At what rate is the angle between the ladder and the ground changing? Now we want the d O over dt. All right. So somewhere we got to make an equation to identify this. Now, let's make it easier. Let's just define one of them. Okay, and we want it against the ground. So the ground is x. So what value gives you x? What is it? Sine? No, it's cosine. As possible. So we're going to use cosine of theta equal to x over, what is it? What's the latter? 10, right? Yeah. Theta is adjacent over hypotenuse. SOHCAHTOA. But we're going to get there. All right. First, we're going to take yes. Okay. I'm going to have negative sine of theta d theta t equal to 1/10 of dx dt. Did I lose anybody there? Okay. Now I'm going to do the substitution. So I want sine of theta. Sine is opposite, which we said was 8 over hypotenuse, 10. And that's going to give me 4/5. So it's a negative 4/5 for sine. Okay, and then I d theta over dt. On this one, I have the 1/10, and this guy is 8. Are we good? I'm making sure. All right. Now, okay, let's do a little bit math. I'm going to multiply. So 1/10 makes it 4/5 times a negative 4/5. Oh, busted. Yeah, it is. It's a reciprocal. Golly, I was dividing and I multiplied without reciprocal. And I'm going to get a negative 1. And we're in radians, so it'd be a negative 1 rad per second. Thank you for that. Here we go. Are we good? This one here, we've got a sphere, a balloon. A balloon is always fighting gravity and fighting the pressure within it. It looks for equalization. So, a spherical balloon is inflating with helium. We're growing in this case, right? Inflating at a rate of 64 pi feet cubed. So this is what a dv dt is 64 pi feet cubed. Because we can only have feet cubed in volume, right? Okay. How fast is the balloon's radius increasing? dr dt when r is 2. Right. So this is our known or given. That's what we have. We have to find the formula for a sphere. There it is. 4/3 pi radius cubed. So we're going to take our derivative in terms of time. We're going to put in everything we know. We're going to do simple math. We're going to divide by that 16 pi. I see that's a pi. Now what is that? 4? So this is changing at 4 feet per second. It's inflating. The radius is growing. All right. How fast is the surface area? Oh, baloney. I think it's 4 pi r squared. 4 pi r squared. Yeah. All right. Going to do the derivative. Okay. And we're trying to find surface area increasing. So therefore, we're going to substitute the r and the dr dt. Our r is 2 at the point of this evaluation times r 4. And this is in feet squared per second. Oh, oh, seconds. 4 feet because we're referring to the radius, not the volume. How we doing? Fun stuff. Clear cut. I'm going to stop right there. We'll start on Thursday there, and we're going to finish with linearization. Linearization is cheesy easy. It's not a big deal. So don't get ahead of me. I'm going to cut some of the problems out. So don't work on 11. Thank you, gentlemen and ladies. You are outstanding. Thank you very much. I didn't do the roll, but I just know one's missing.